implantation. This is next set of moments. 3 from diffusion, 2 from implantation. And from a week from now we have exam next Thursday. So this will be due Tuesday after that. This is a surprise. Time's flying so fast. So, yeah, that will be 1st of March, end class, closed book, or you can choose to have take home. So far it's in class. And then term paper is due March 20th. It's probably a good time to start thinking about that and discussing some ideas with me. If you feel strong about something, then you can write some abstract few lines and high level summary and send it my way, and I can give you some feedback. If you have not uploaded your homework 3, you can leave that hard copy here on the table. So I can share some. So there are very specific requirements given in the syllabus. So you have to go there and look at those. Maximum 6 pages. First page should be something that contains the abstract. Should be separate from the rest of those. It includes into the count, but the first page will be something that will circulate amongst the class. And for exam, we'll have till Tuesday is what will be covered. So what we do now is we are starting with iron implantation, so I'm hoping to finish iron implantation by the next lecture. So even if we don't finish, so whatever is we do till Tuesday will be covered in the exam. Some of the topics before you start asking, there are some of the topics some students picked in previous semesters. I'm not saying that these are the best topics or they were better than the others, but these are some of the topics and something that tells that there are many ways of looking at silicon fabrication. Optics, masks, lithography, mirrors, material for gate oxide, and interconnects. This all comes into. So if you look at the titles also, these are not review of something. These are basically identifying a problem and suggesting a solution. So if you are in doubt, read the description in the syllabus. It's supposed to be a forward-looking exercise. It's not a review where you sum up what has gone before. Right? So and some of just wanted to share. So this should give you some idea how to or what to pursue. Again, these titles are not showing them to show my bias towards these or against these. It's just what students have done before. And of course, that taught many semesters, and these are just picked up a few which were easy for me to copy paste. Right? So that's probably the bias here. Right? So, any questions?
So should it be group work or individual work for term paper?
It's an individual assignment. Yeah. So what you do on this date, this will be the deadline for your paper. So whatever you decide, all the discussions that need to be done between you and me have to happen before that, right? Because that day you upload your final finished product, which will be a PDF or a Word document, right? No JPEGs, no DocX document or PDF. So before that, we need to discuss. If you have some ideas, concerns, talk to me now. Start that discussion now. Some of you have started that discussion. Let me tell you that. And historically, those who have discussed the ideas with me have fared better. Not because I can I try to direct, but because I can give you some feedback early on, that if something is worth trying, or what would be the right way of approaching a problem. So I can help you with the process to succeed, not actually with the content. Content is something that you have to develop. I'll help you with the process. Right?
Sir,
Yes, ma'am.
if the midterm is a take-home, will it be due on the next last day?
If you guys decide for take home, I need to hear from each student via email to go for that. Then I'll give you a week. Then I'll shuffle, adjust your homework, and
But
then
we can vote on it now, say we prepare a midterm.
it will be an email that comes from every student. So unless all of you agree, I will not be able to take home exam. So that you'll have to do offline, off the,
So we have to lobby our classmates.
do whatever needs to be done, because we live in democracy. So you have to, if you need to, so this is what I've decided. Default, you want to change it, I'm ready to do change. You gotta gather all the votes for the rest of the class. You guys are meeting Friday, half of you are meeting on Friday, half of you met yesterday. So do whatever needs to be done. Should be, I'll be ready to give you that take home. Then I'll give you a week from the day I get, so the day I post or hand out the hard copy. It will be a week from that you have to turn it in. Right? So that's some administration. So iron implantation, we have discussed some of it. So it's a process in which we want to introduce energetic charged atoms or molecules into a substrate. And more precisely in terms of silicon devices, we want to introduce dopants into a semiconductor crystalline structure, right? It can be semi-crystalline, but the idea is introduction of dopants, which would electrically change the behavior, change the electrical behavior of that substrate. So this is just an example showing a wafer and an electron beam which is being bombarded on that level. So these are all wafers which are probably coming in front of the beam in the turn and getting bombarded.
There's an actual picture, not a conceptual one.
I guess it's an actual, because it says Eton He3 high energy implanter showing the ion beam hitting this wafer end station. So I think this is the real thing. So the beam is very tightly focused. So what are the important parameters in such a process? We have a beam which is composed of charged particles, atoms, ions, molecules, and when they travel, what do we call the travel of charge? We call it current. So, and that covers certain area, and it happens for certain time, which results into the introduction of certain charge into that substrate, right? So we call it implantation dose, which is implanted ions per unit area, atoms per centimeter square. So if you draw a relationship, so that would be integrating that beam for the time it takes, charge is constant, area is constant, m is a factor which is mass of the ionic species. So these are constant. So what matters is how long do we bombard that beam on a surface, right? So a closed form is simple IT over QA. Q is the total charge. So when we have the device ready for the process, we end up putting some hard mask, right? And the mask may itself be something that can have specific thickness to it, or maybe it's just an opening. The thickness will define how deep we want the profile to go? How deep do we want those ions to travel within the substrate? And a thicker mass would be where we want to arrest them. We don't want them to go inside. So this is an example of where we have silicon dioxide on top of silicon, right? So now, how can we make such a structure?
Surface micromachining.
Surface micromachining. Okay. So we can just do silicon IC fabrication, right? That's also right answer. Exactly how do we do that? Let's be a little precise. Pardon?
You etch it.
Etch it. Okay. Let's take a step even further back. What would be the first step we would want to do?
You define it.
We would define the area we want to etch it, right? So if it's silicon dioxide, simple photoresist is going to give us that area where we can do that. Right? So that's fine for the top, but if you look at that particular feature, the oxide has a profile within the silicon itself. Right? So I agree with you, we can pattern from the top, but it seems there is a pattern on the lower side as well, at the interface of silicon.
I remember something called low-cost process.
Low cost,
Yeah.
right? It's not remember, we have taught you that.
Yeah.
So you have to remember that, because week from now, I'll be examining you on those things. So what a simple thing can we do to get this kind of profile? The first question, will we have to do something to get this profile towards silicon first or towards the upper, away from silicon? What would be the first step to do this?
First, it would be to make a thin layer of oxide. Then
First would be to make this profile in silicon. Different oxide depth in silicon. And then we can do pattern on the top and do that. You won't have to do that because in low cost what we can do is we can deposit silicon nitride everywhere and pattern nitride. Right? So now once we have patterned the nitride, so if I have silicon dioxide, silicon, and a pattern silicon nitride, right? And then I can do oxidation, and this guy is going to just become thick, right? So this is all oxide, and then I can remove silicon nitride. What I'm left with is something like that. Make sense? How can we remove silicon nitride? Phosphoric acid, just phosphoric acid, boiling phosphoric acid, boiling phosphoric acid. We haven't done etch yet, have we? Have we done etching? No, we haven't. We just looked at the process. We haven't. Yeah, so we can remove silicon. So this is one way, but we can use photoresist also. Can we? Yeah.
why is the implantation dose measured with atoms per unit area instead of atoms per unit volume?
Yeah, volume. Yeah, that's a very interesting question. Before the dopants get incorporated into the substrate, all we can control is the area where we impinge them. Once they get inside, yes, now their profile is what we will see many models. How do we explain that? So then it is a three-dimensional problem.
So the doping concentration will be measured with atoms per unit volume
On a surface.
Yeah.
So it's not doping. It's the dose of the beam
Okay.
which is striking the substrate from top, and all we can control is how much reach in a cross section, right? And then how deep they go within that cross section. Then the depth would be the third dimension, but that would be within the substrate now. That is not a function of the beam itself. That is a function of the beam itself, but there's much more that comes into play once you talk about substrate.
So implantation dose is kind of a parameter for the equipment that we are using.
Of the
for
beam.
implantation.
Of the beam. Simple. Because beam is striking in a 2D area. Can be, right? But once they get incorporated into the substrate, then it's a three-dimensional problem. And then it starts so simple, just because when we strike the beam, it's in vacuum. There is hardly any resistance or hardly anything that impedes the flow of ions. But once they get into the substrate, the physics changes. So then it's a 3D distribution problem. Right? So what are the advantages of diffusion? We can control the dose. We can control exactly how many dopants do we strike. Unlike diffusion, where it would be a parameter of how much cross the boundary, right? Here we know how many would cross the boundary because our dose is what we can control. They have less lateral distribution. Simple reason is it's like firing a gun, right? So they have energy that they lose while they are traveling within the substrate, and that kinetic energy lets them go in a straight fashion. There is just lateral distribution, but it's way smaller than diffusion. Right? Of course, there will be collisions, and that's what causes them to come to rest at certain depth. But that is much more travel is vertical than lateral in this case. And we can control the profile by controlling energy and doing multiple implants at different energies. So when you say multiple implants in devices, in modern devices, we don't have just one doping into a device region. We have multiple regions of doping profile. And part of the reason is to get rid of short channel effects, to alleviate the issues that come with those very miniaturization of those devices. So this is a very crude way of saying that we make source and drain. This boundary is not as precise to start with, but now what we want to do is we want to make these regions of different doping density going away from our main area of interest. So that may be 10 raised to power 16 here, 10 raised to power 17, 10 raised to power 18, done by successive implantations. Right? So the part of the reason is if I want to do this much in one go, I will end up with much more lateral diffusion with that. Instead of that, it's done in what you call superimposed multiple implants at different energies. And very interesting, very important part, it's a low temperature process. When it's a low temperature process, I probably don't have to grow oxide and do etching. All I need to do is apply photoresist, do lithography, I'm ready to do implantation, right? Because resist can withstand. There's no issue of resist degrading with temperature, unlike in diffusion. So it's a low temperature process, which means less cost and high throughput, right? Then these can be introduced through thin surface layers. So can be confined to very thin region close to the surface, which we couldn't do with diffusion, right? And the profile is abrupt; it falls down quickly. But we can't do that in case of diffusion. There was a tail part to it, right? And now because it's low temperature, it's something which many more types of materials can be used to use it as mask. and what we call self-aligned implants. So having structures on top can result into exactly where the implant will go. So by placing these masks, we can make them go exactly where we want to go.
So you can avoid bird's beak like this, or
Pardon?
a bird's beak. Bird's beak that forms between the source and the drain. It can be avoided completely by this, or there will be some effect.
Bird's beak is formed in silicon dioxide. That's
Yeah, but since you are defining like a vertical trench, so
Right.
can that be eliminated using this method?
sort of, we're not creating any trench. There's no physical removal of material here.
I guess what we're asking is, does this avoid the bird's beak?
Bird's beak is not a function of doping, is it?
No, not a function of doping, but like.
You're concerned about lateral
Yeah.
straggle or there is lateral travel of ions still
Yeah,
in
but
this case.
could this be applied to even silicon dioxide method? It does not apply there.
Silicon dioxide method.
Okay, I'm not being very clear about this. You have the tapering edges at the oxide, right?
Right,
If
right.
we use something similar to iron implantation to do
Right,
that,
right.
would you be able to eliminate that? Like if you use this method of.
Okay. So that those bird beaks and silicon dioxide are not a function of dopants,
Okay.
right? But you want to eliminate those bird beak
Yeah.
by implantation. By implantation works with incorporating ions into silicon. How is that related to?
Not exactly implantation, by defining like the method that we use for.
So bird beak can be used as a mask. That's so silicon dioxide, any structure can be used as it is used as mask material. They can be used to confine the lateral
Yeah.
dimension of the dope area.
But it won't. But it will taper at the edges, right?
So you'll have less amount of dopants
Yeah.
going through, and gradually no dopant at
But
the
it won't
edges.
be a straight vertical line.
It's that's something which we'll see. Can we have when we say abrupt profile? How abrupt is that?
Yeah, that's
It's-
what like.
It's always a Gaussian distribution.
Yeah.
So hold on, just hang out with me, and you'll see. It's when you say abrupt, it's not a 0 or 1. It's not digital. There's still many factors which come in because it's physical bombardment and physical collisions will cause them to go any direction. So,
Right.
yeah. So however well defined your mask is with bird beak, there is always going to be a distribution.
Okay, so it does not matter if you use diffusion or an implantation. That curve will always be there.
But how steep?
Steep.
That would what define how steep. Which one is more steeper? More steep. So it's done at vacuum, so low contamination, but it causes damage to silicon, which is obvious when we are doing bombardment, when we are incorporating, we are forcing them to go inside, they cause damage. And damage and for crystalline silicon is knocking off of silicon from the lattice structure, right? But we regain that, we heal it by temperature treatment called thermal pinning, which gives them enough energy to come back to their latest positions. And how deep can we do it? Is rather shallow than diffusion. In diffusion, you keep it in the furnace long enough and you can go as deep as you want, right? But here there is certain depths that we can go. 1 micron for conventional implanters and what is called high energy implanters is 4 micron. That's as deep as we can send them. And it has lower throughput than diffusion, but it's not too bad than what other things that we do. And the simple reason is that we have to do an annealing process after implantation. So implantation itself is a fast process, but then again we have to expose it to high temperature, so it reduces throughput. Complex and expensive equipment. Simple reason, you have now an iron gun, then you have column where you have to focus that beam, right, while maintaining vacuum, and you have to then make sure the beam travels into a very, very narrow, what you call, well-defined area when it strikes the wafer. So that brings in the complexity into the system. Safety hazard gases are toxic, voltages are high, and parts move rapidly. There's a picture given in the book on the different parts of the planter. We'll also see some on that. So this is the three-dimensional distribution. And there are many models that have been defined to understand or to predict where the dopants will go at a given condition. And with respect to depth, in a three-dimensional system, they would have distribution which will be not only in x direction but y and z as well, right? And we can, to first order approximate that, more is the voltage that we use, the deeper it can go, right? But the deeper you want to send them, there will be much more collision that it will face. So the concentration of dopants is something that we have to compromise them, right? So this defines the boron in silicon at this dose. So different voltages give us different profile. When you say profile, it's depth and the concentration as well, and the breadth of the, what you call, Gaussian distribution. So this gives a very well confined distribution. As you go deep, the distribution becomes too wide. From device point of view, it would depend on what is our application, how heavily doped we want this to be, how deep we want this to be. It's a trade-off that we can't have both of them. And the part of the reason is there is some things that we have to define. There's one distance which is called the range, that how far does it travel, and the other one is this range parallel to the incident beam, which is projected range. We think it's getting into certain depth, but then actually the doping profile extends beyond that range. So these numbers are important because the physical collision causes the travel to be different for different ions. So they lose energy due to collisions with nuclei and electrons, and eventually they stop. So RP is what represents the average depth below the surface that an ion will penetrate. Not every ion will penetrate to the same depth, so that's why you have to define an average. With average comes, when you take average of some numbers, what is the other important factor you need to know?
Deviation.
Deviation. And what does deviation tell us about average?
From the way how
So your sampling numbers, how far varying they are, right? So is it good to have large deviation?
no,
We want it to be
it's close.
narrow, so the average is a closer depiction of the actual range of the. In statistics, all these numbers mean specific thing. Range is specific, mean is a specific, median is something, means something. But generally, we take average and then we are concerned about standard deviation, right? In this case, for each ion traveling to certain distance, maybe ending up here or here, we would be defining something called straggle. How far they fall away from this mean, right? Call it straggle. So that's a delta function. So known as the projected straggle. So that's the fluctuation of depth along the direction. But then there is a fluctuation perpendicular to the direction as well, which is called lateral straggle. So both of these are important because once we bombard an ion beam, with that choice of good color, something which is strictly different. So what do we get? We get not only distribution in ionic distribution in the concentration of dopants, right? But we get the distance also, which increases or decreases depending on these two straggles, delta RP and delta R perpendicular, right? So this guy is perpendicular to the flow. This guy is in line with the flow. So, and this is a projected range. And then this is N, and this is 0.6 of N. We'll see which number is relevant for us, 0.6 or just N. Right? So make sense? Now, two ways how do they come to rest. One is collision with nuclei, and the other one is collision with electrons. One is a process in which energy is lost from nucleus. The other one is energy is lost because of electrons. So both of these can be defined as S sub n, S sub e. So we'll see how this definition comes into play. But the idea is that we have to define the energy before it strikes a substrate, right? So for different ions, it may be where this guy is more prominent or this guy is more prominent. Now, conceptually, why would they differ? Energy lost to a nucleus or energy lost to an electron? Why would they differ? I can pick up a fight with this guy, but I don't want to pick up a fight with that guy. Simple reason is mass. So nucleus and electrons. So don't worry, I'm not going to pick a fight with you. But that tells us that depending on the ion's interaction with electron, the nucleus, it will define who is the major energy loss mechanism, right? If it's electrons, it can probably penetrate further because electrons have smaller mass, right? And nucleus is way larger, right? So that's why we want to define this, and then we'll see how it varies for different materials. And that's part of the homework also. You do one set of calculations for one type of dopant, and then for other one it's different because these factors will be different. But the combination, their addition will be what we call total energy. And the distance that an ion travels can be measured from calculating distance from 0 to the total loss of energy, right? It's going to keep on traveling until the energy becomes 0, right? So this is something, then dr is factor of E naught. How far it goes will be defined how much energy it has to give, right? So now, if I am the ion and I am striking, and I have different mechanisms to lose energy for electrons or nucleus, my penetration depth will be different, right? If I lose much more to electron collision, then I can travel further. If I lose much more to nucleus, they're going to arrest me much sooner, much shallower. So, E naught is initial incident ion energy. So, if I have more to contribute, I'll travel more. If I have less, I'll travel less. But then again, what is the mechanism of loss of energy that will define how far I go, right? So, model would be a simple model, much more accurate. There are other models also. It takes into account a factor called Ke, which depends on masses of ion and the target atom, right? And it takes it like a projectile in a viscous medium and defines how far it will go before it comes to stop, right? You can ignore this, but the idea is that it's just atomic scattering potential due to their collisions. So what this gives us that nuclear stopping increases linearly at low energy and it reaches a maximum at intermediate energy, and if you have much higher energy, then nuclear stopping becomes almost negligible. So depending on what energy does it start with, that defines how fast, how far it will let them go. So ions move past target nuclei too quickly before it can transfer energy. They're too big before they let them completely transfer. But nuclear stopping increases with heavier ions. So depending on what kind of ion we are using, nuclear stopping will become more dominant. So electronics stopping is more simple, more energy you have, right? And it's independent of mass, right? So what you call crossover energy, where this loss to electrons, the loss of nucleus is what you call, it's higher for heavier ions, because for heavier ions, it's the mass that matters, not the charge, right? So this explains it well, that you have boron going to silicon, phosphorus, arsenic. So E1, which is nuclear, and E2, which is electronic, they have very different behavior for these guys, right? And this as well, have nuclear stopping, electronic stopping. So if you look at boron, the more energy you give it, all stopping is electron, not the nucleus, right? But if you look at the phosphorus, you see that the crossover occurs at much higher energy, right? For boron, it starts at 10. For phosphorus, happens somewhere there between 100 and 50. As process ingredient, now you have to know. Probably you won't do anything because there are set recipes that we use. Recipes tell us, okay, use this kind of energy, this dose, this voltage, this thick of your mass material, how deep, of what concentration you will get. So these are very well defined. If not, you do characterize your equipment and you come up with those, right? So this is the physics behind that, how these differ for different types of domains. So using that assumption, playing around with those equations, we get something which is called RP, that what's the projected range, right? It's a factor of incident ions, target ions, and the actual distance that they travel, right? Now, when we discuss distribution, can we take average? When we want to define distribution of particles in this case, how far they travel, we need to know average and deviation, right? Both have to come into a what you call model. So, and that can come from a Gaussian curve, a symmetrical Gaussian curve, where we have distribution on both sides of the peak, right? So it can be either way, but the idea is it has to be symmetrical, only then we can get a close formula for the distribution. So the implanted concentration and calculated with these guys. So this is an exponential function, right? So n is the number of ions at x depth. It will be an exponential of minus x minus RB, how deep they go, minus projected range, right? And delta RB is this taken from that line, right? So this is standard relation that we use to measure how far it will go for a given dose. So I had these slides from past where we were using phi, but this book uses Q as the charge, as the dose, right? So from this guy, we estimate how deep this goes. There are models where we plot them, that gives us these relations which we can use to get our recipe, right? So in both cases, so as when you do your process, you will use these charts to define your energy based on the depth you want, right? So if you use an energy to figure out how deep you have your profile, you use these guys, which are calculated from that relation, right? So this discussion again, the charge is how many particles are there from 0 to infinity. If you contain it within silicon, then the relation confines to just this guy, which is the delta function of the projected range.
What's phi again there?
Phi is your dose. Q or phi is the same dose. Right? So for an infinite system, this would be the relation. Just count how many of those ions are there, right? So that is your total dose. But for an implanted dose within silicon, that reduces to this guy. And if you look at this relation and put value of Q here, this relation gets further simplified to something like this, right? Where you just have for projected range, we end up with relation which is just Q times Q over 2 pi of straggle of the projected range, which further simplified gives us 0.4 Q over delta RB.
So what's x again for this? Is that the distance?
X is the distance. So if you take the projected range, this becomes to a very simplified relation.
I see. So for this is for where x is at the peak. So you're assuming that the peak is where you're taking your x for the calculation. You can just say.
So your relation becomes simplified. Now, why 0.4 Q or P? If you remember that own relationship, so that's where the maximum will occur. 0.4 of Q. So when we are doing relation, so this is calculation of simple dopants in silicon with LSS. So this is arsenic, phosphorus, boron. Right? So with energy, you increase the projected range, right? And for that range, you can figure out the straggle in both directions, right? With perpendicular as well as in the direction of the incidence of ion, right? So if you know this, then whatever your mass is, the thickness of the mass will define how many ions pass it through. So at each thickness of your mask, if it's a thinner one or thick one, how many make it through, and what would be these two guys, they'll be different at different points, right? How much energy they have while they get into silicon, that will define what point you have to use based on the energy of the size. Does it make sense? So you can use bird beak to get something like this, where you have graded profile, right? Because we want graded profile in many applications, where we don't want abrupt profile. So that case, maybe you want to play with that and get different energies of ions when they enter the substrate. Make sense? Many questions? What essentially you should be worried about is reading these charts, knowing, if understanding the question and knowing where to look for the answer. I hardly ask you to derive equations. I would want you to know and be comfortable with these things. This straggles and the range of the total, right? At different energies. So if I give you a dose, you should be able to figure out the energy. Not a simple relation. On first few slides I showed that how do you relate Q with current and with time, and all those things, right? So there are different target materials which have different projected range and different straggle for different concentration profile that we need, right? So the more the range, the less the density, right? Of course, we saw that you can increase the range by increasing the voltage that you apply, but that's going to reduce the concentration. Okay? So in this case now, we see for 100 kilo electron volt for boron, how do the range change in different materials. So this should tell me if I want to use, if I want to do it in silicon, what kind of material do I want to use for my mask, and what thickness. Does that make sense? So if I want to define something which is 30 nanometer deep in silicon, how thick of silicon dioxide I have to use to be used as a mask. Make sense? Do you understand what I said? So, okay, I know in boron at 100 kilo electron volt, right, which is the headache, how deep it will go into one material, which is the projected range, RP, right? And then what would be the straggle, which is delta P, gamma P, what is this called? Sigma P, right? So which is delta RP, which I have, right? So now I want to use some material as mask, which means that boron should not be able to pass through this guy, right? But of course it should go through this guy. And I want to say make something 30 nanometer deep in silicon. So if I use silicon dioxide, how thick do I have to make this mask? Because I know it has more penetration than silicon, right? And I want to make this guy 30 nanometer or whatever unit used. So how thick do I want this guy to be? How thick of silicon do I need here? Silicon dioxide do I need here? What should be this thickness, at least? More than 30? More than 30? I would say 10%, 33, right? 33 nanometer. But then this is also something important. It can go to 3666. So what do I want this to be? 40 nanometer, right? At least 10% above that it can, one ion can pass through, right? So to make that 30 nanometer depth, I want to use silicon dioxide. Then this plot will tell me how thick silicon dioxide should be to be used as a mask, a reliable mask. It can be used mask even if you use 20 nanometer, but reliable mask that no ion passes through, right? Or negligible ion pass. Does that make sense, guys? So can expect something like this I would expect you to know how to figure these simple things out. Figure out upper limits and lower limits on these guys, right? So here we are talking about lower limit. At least it should be, I would just add these two numbers, that will be my upper limit, right? Upper limit of how deep ions can go through. That should be my lower limit of this thickness, right? Make sense? So this is something that tells us what material can be used. Ideally, if I had my way, I would use silicon nitride because photoresist is crazy. It's like how much? 3 times than silicon, right? But then, if you are process engineer, what would you do? Would you want to clean your silicon wafer and do an oxidation run for, I don't know how long it's going to take to grow that much oxide, 40 nanometers, maybe it takes 5 hours, right? Or you just want to coat photoresist, which is going to take maybe half an hour, right? But now, in photoresist you can coat very thick, right? Simple. Have you guys done lithography yet? Okay, that's someday coming next. So it's very easy to coat 1 micron thick photoresist, right? So I might want to do photoresist if I can. Because 1 micron is thick enough, right? How many nanometers there in 1 micron? Right? So that's gonna need 10,000. So I need 10 micron. Right?
It's 10,000 ions.
Oh, that's extra. So 1 micron. So this is 1 micron. Yeah, so I could just have 2 micron and that'll be good enough, right? Or 10%, 1.1 micron. Right? So that's also the trade-off. Do you want to do oxide mask or can you just. So this is entirely different parameters than diffusion when you're doing ion implantation. Right? So this is now for donors and acceptors, phosphorus, arsenic, and boron and gallium. Same concept, now little more precise data. So this is all known. Now for you to look up when you're defining your ion implantation recipe, you don't have to calculate all those stuff either. So all you would have to know is for how deep you want it to go and what concentration do you want. What mass material you can easily apply, right? And that would define your process, right? So these are again range and sigma. Of course, we see that in this case it's much more. In this case, the sigma does not change with the range of phosphorus. What can be a simple reason for that? You see that this guy changes over the range, but that guy is fairly constant or consistent with it. Depending on what is the energy mechanism, what is the energy loss mechanism will define how much would be the straggle, right?
The size matters.
Of course, because for SE, size has no value. Doesn't matter how big of the ion is. If the whole loss mechanism is through electrons, size doesn't matter.
So boron
So,
will have more of SE.
so exactly. So now, if the size of the ion, if it's losing the energy to nucleus, then of course the size matters. So that then it's a factor of what is the loss mechanism, right? So that will define the straggle. That in a way tells us which shows more sigma, more straggle. That, right? So others, fluorine, oxygen, silicon, argon. But if you look at the ranges, that's why we call them fast diffusion, right? They go through quickly. Oxygen at say 100 can be 2500 angstroms, right? And at 100 it's barely less than 1500. So oxygen can be implanted way fast, right? So they can penetrate really well. So that. But of course they may not be used for doping, but they're done for other reasons. Why would we do oxygen implantation? Why would we want to do oxygen implantation?
To do buried oxide.
To do buried oxide. And what does buried oxide do for us? Forms an insulator embedded within the substrate, which means
It is stuff.
pardon?
It's stuff layer.
It's an edge stop layer, right? And it basically isolates the top from the bottom, right? So if you're making devices just on the front, now what you can do, you can make devices on both sides. This is what we call SOI technology. That's what they use in industry. They use silicon on insulator. So it can give us what we call silicon on insulator wafers. So the idea is you have silicon and then you have this buried oxide. And of course we know ion implantation cannot go too deep, so it is close to the top, but it's called buried box, and this is called SOI layer. This is called bulk silicon. So these are, if you look at them, they are normal wafers. They're just silicon wafer.
What's the difference between this and growing an epi layer? You can't do it on top of silicon.
For epi, you need a crystalline layer below to grow it. You can probably do it, but this is much more simpler than epitaxy. It is much more simpler. Just implantation is much more simpler. So what we do is, okay, you guys have seen wafers now. Right? So if you hold a silicon or SO wafer, you won't be able to tell because the oxide is embedded in below. And we know that we can't do too deep of implantations. We can't do so. It's about 2000 angstrom deep, 200 nanometer deep. What it does is, and then we can define how thick of box we need, right? Because the more it is, the higher energy we have to do, and there will be more straggle, it will be more wide. And then we can make devices on top, at the bottom. We can do etching in silicon, and once the etchant reaches this layer, it's gonna stop there. We call it etch stop layer, right? So it's gonna act. So this is one very common application of oxygen implantation that we do. So there are other models that define many different phenomena. So they account for non-Gaussian distribution. So we get Gaussian distribution, but if you consider the backscattering in the for ions like boron, there is much more, the profile of Gaussian distribution is much more skewed towards the surface. Instead of perfect Gaussian, for which we could use that simple relation where we said it's symmetrical distribution, but it's not symmetrical for all of the dopants. It's skewed towards. So then we use different models to explain that. And for heavy ions, there is no backscattering, so they are skewed towards the other side, towards the bulk of the substrate. And then there is a factor called channeling. We look at channeling where they can just zip through. They don't stop, so they continue to higher depth. So that's called channeling. We'll look at what is channeling. So there's one model called free moment. It shows two half Gaussian profiles. So each has its own RP and delta RP, right? So instead, a perfect Gaussian is where you have same profile on both sides, but they're defined separate for both sides of that peak distribution. Four moment, where then they bring in other factors like skewness, or Quatos is more of tail of distribution, that how far it goes and how quickly it falls off, right? So if you look at a profile, there are, so far we just looked at this guy and probably said, okay, which one is, right? So now they are looking at many more details, how quickly it falls off, how far it goes off from, right? But we'll stick to that first model that we looked at for practical applications. There's idea that there's no skew, but in this case there is skew, which means that the distribution is changing. For this side, it's much more
Skew.
ahead.
Rightly so.
Huh?
Rightly so.
It's what I don't know what is it called, factors. But the idea is that it's not symmetrical along the maxima. It's much more, what do you call it, ahead, away from the center line on one side. So this zero skew would have certain shape. So this is now when it has skew towards the front, right? So because of backscattering, there are many more which are towards the front than towards the bottom. And again, it's the same idea that with voltage we are increasing the depth, right? Boron. So that's if it was a Gaussian, it should have been like this, but what we measure and the model shows something like this. That's for boron. So then they define skewness for them for boron. I think it's all for boron. They're all for boron. Anyway, that's if you look at much more closely, then there are many more issues with that. Monte Carlo is a set of equations which are solved consistently with each other. So that takes care of the history of one ion and calculates its paths. And that considers a simple binary collision where either it will deflect or it will continue straight. And that gives us a history for all these number of ions, that how would they behave. And that gives us a very well-defined distribution. And so this Monte Carlo simulation is where we take one particle and we define its motion and we measure that motion, and ultimately once we have n number of particles, we see their collective behavior. Right? Okay, channeling. So in the LSS model, what we defined was a very well-defined target material, right? Where oh, it was not, it was amorphous, where there are randomly placed atoms that would result into the collision. But what actually we get is a silicon which has order, which has, so to speak, empty spaces in between, right? When you have a lattice unit cell, you have 4 atoms on the top level, 4 atoms at the lower level, and this building continues on. So if I'm standing in the center and look up, I don't see any atom, right? I can zap through that. So this is what gives rise to the idea called channeling. So it doesn't stop. It doesn't come into contact with nucleus. Nucleus doesn't strike to electron, wouldn't lose energy. So what we see is many more of them resulting into this tail, which is non-ideal, which goes away, moves away from Gaussian distribution. So they sneak through their way to pass through. So in a random orientation, there will be equal probability of finding for every ion, equal probability for their collisions, right? With collision losing their energy. But in a very well-defined structure, some of them can zap through. And that is also a factor of the crystalline structure. If you have 110, it has many more open spaces than 111 and 100, right? So they would result into different channeling. So this would be different. What you call channeling tail would be different for different orientations, right? So we have seen some of things where the orientation mattered, right? Did it make difference in oxidation?
Yes.
Right? Did it make difference in diffusion?
Sure.
Sure. I didn't see orientation anywhere in that diffusion equation. Did we?
I thought it was one of those processes that was sensitive to orientation.
Okay. So probably time to revise those things in next week or so. So there are certain things, certain processes which are very specific or they depend heavily on orientation of the element. Some they don't depend heavily. They show some differences with the orientation. Some have no effect with the orientation. Even in oxidation, if I do wet oxidation, that's so rapid, essentially my orientation doesn't matter there, right? But in dry oxidation, it would make a difference, right? So not just the process, the end product would also be different based on orientation. So this is another process which has some non-ideality that changes, that differs with orientation. So these are now, okay, now we have seen LSS model, now we are looking at non-idealities. What are the things that are actually different in application? So for different orientations, we see, these are not orientations, these are the angles, the beam angle. Yeah. So generally, we take it as a standard, but if you are very concerned about how deep your profile should be or how well confined it should be, we define our beam angle. We tell normally their vendors, we tell them what angle do we need for them to do ion implantation. If I use 100 wafer or 111 wafer, the angle is very clear, right? The data is known. What kind of, if I have 111 wafer, I will know, and I'll be careful to define my angle, because that will define how well confined my implantation is, right? Now think about it. If I have SOI wafer and my SOI is 200 nanometer, do I really care how should be my orientation. Right? Depends on how deep I want to do it. If I want to dope, it's micron. So up to this part, I don't care. This is less than 200 nanometers. It's clearly visible that it doesn't matter for me. Right? Make sense? So if I have SOF and my silicon is 200 nanometer, my silicon that I really want to dope is just 200 nanometers. Do I really care? No. But if we are using a wafer and we really are concerned how deep it should go, we have to define our angle. Right? So if you see this plot and I want you to define all the parameters for an ion implanting and ion implant technician, this should also be one of the things defined for the technique. Right? So this is a 110 axis in silicon. And you see this, all the way there's nothing. Reminds me of that air duct in Mission Impossible 4, right? In India, he jumps, has to jump. So, but those ions can zap through this guy. Right? Any questions? So we can use it to our advantage if you want to implant it really deep. But then we have to control our angle. So we have to know that exactly, because you saw those angles are 135. Just an anomaly of 1 degree will change the process, change the end product. Right? Have to be very well defined how deep you want to go and what angle you want to use. So in this case, we see there's channeling through screen oxide. So we have an oxide at the top and we see how deep it goes. So this is for phosphorus, P-type silicon. No, it's phosphorus, it's not P-type. We can go down to 12 micron, which is really deep. For device point, it's really deep. So we can use channeling to our advantage. And we, just to get rid of any channeling, we give large angle, 7 degree of bond. And we give a screen oxide. Right? So this is again angle which tells us for different types of wafers what kind of angle would be needed and what energy would be needed. Right? Questions? So should be able to cover those questions of homework.